Hi, everyone. Thanks a lot for watching this talk. This talk is about bypassing the surface embedding, approximation schemes, and for network design problem in planar and minor graph. This is a paper that will be presented at STOC 2022. All right. So in this talk, we are trying to understand the complexity of some classic network problem design on minor free graphs. So what's the global scope? The global scope is that given a metric optimization problem, namely an optimization problem that is happening on metric space, one can try to understand the complexity of this optimization problem as a function of the underlying metric space. Maybe this problem is going to be hard on general metric spaces, but if you start constraining the metric space, maybe it can be like a low-dimensional Euclidean space, maybe it can be a tree, maybe it can be a planar graph, then the complexity of the problem is going to change, and the problem may become easier. So, for example, many of the network design problems, for example, traveling salesman problem, become very easy if the underlying metric space is just a line. And then one can look at the complexity when it's plane, when it's a planar graph, minor free, R3, R4, doubling metrics, and so on, until the general metric space where it's a harder problem. Good. So in this talk, we are looking at network design problems. So what is a network design problem for us? It's a problem where we're given a set of points P in a metric space, and the output, you can see the output as a graph where the vertices of the graph are the points in your metric space, and you are asking for connectivity, for some connectivity pattern on the point P, which you represent with the edges of a graph. And the goal is that this graph that you output satisfies some property. And the objective is to minimize the length of the graph, where the length of the graph is given by the distance between the endpoints of the edges of the graph. So for example, if I give you a set of points in the metric space, I want to solve a traveling salesman problem in this metric space, I'm looking for a graph that is a tour, and the length of the tour is just the length of the edges of this graph. And that's, so this notion captures the traveling salesman problem. If you're looking at, for example, Steiner tree, you are given a metric space, you are given some specific subset of the input points that are the terminals, and you are looking for a tree that connects the different terminals. So that's the graph you're looking for. Okay, KMST, which is also an important problem in this talk, is similar to the Steiner tree problem. The solution here should contain k vertices and should be of minimum. So you're simply looking for a graph of size k. So the connected, so a graph over the point of the thing, but the connected component should have at least k vertices. One connected component should have at least k vertices. Okay, so this question of how hard is a metric optimization problem as a function of the metric space has been widely studied. It's a very basic question, very fundamental question that allows us to both learn about the problem but also the metric space. So that's it's a very nice question. So this is a very non-exhaustive bibliography and list of important papers. There are many other important papers, but I think it's important to see that this question was titled even in the 70s, where Richard Karp was trying to see the complexity of the traveling salesman problem as a function of in the plane, and was getting an approximation scheme, so much better results if the input was, for example, random uniformly on 0,1 squared. Then 20 years after that, there was this very fundamental result by Sanjeev Arora, who showed that you can get actually a polytime approximation scheme for worst case input on CSP and many other of these network design problems for low dimensional Euclidean space. So covering many of these problems. And the question then, one very nice step after that was the result by Kunal Talwar, who showed that you can actually bypass the embedding, the actual embedding in the Euclidean space, the actual location of the points. You only need that you cannot pack too many balls of radius half in a ball of radius 1 in low-dimensional space. That's the only property you really need to get approximation schemes for this type of problem, for network design problem, but also like facility location and so on low-dimensional metrics. So you can go beyond the Euclidean space. You can have a slightly more general metric space that is also low-dimensional in some sense and get approximation schemes. So that was the generalization of this. Another way to try to generalize like Aurora's result is to look at more graph metrics, like graph metrics, for example, planar graphs, so graph that you can draw without crossing in the plane. Well, Philip Klein showed that you can get a linear time approximation scheme for TSP, and that's like 2005. And then from planar graph, you can try to generalize this again to a different class of graph metrics, which are minor free. And these took another 15 years to get to basically TSP. It's subset TSP, but that's really the spirit of it. It's like to get TSP work in these graph classes. So it's a long process to digest and understand more what we can do in these slightly more general metrics and for these different problems. So if we look at these, maybe these three results that are very fundamental here. So the Aurora and Talloires results are essentially frameworks. So they give you a way to solve many problems at the same time. So in fact, you can get one perceptual approximation schemes, but the running time is going to be quasi-polynomial as a function as a dimension and so on. So it's not, you know, polytime, but it's like quasi-polytime, 1 plus epsilon, but it works for many, many problems, and it works for Euclidean inputs and generalized by Talloires to doubling metrics. So it's a general framework that gives you a very specific way of solving the problems. In 2005, Klein showed that you can get a 1 plus epsilon approximation scheme for TSP in linear time, in fact. So it's a different thing. It's like overfitting to the problem. I mean, it's not overfitting, but it's like solving TSP only, but getting linear time. So very efficiently solving something for a very specific metric, which is planar graph. And it doesn't work for minor free, for example, or even for surface embedded graph. Like if you embed it on the surface of bounded genus, you would not get, you can't make it work directly. You need more work. Okay, so the outcome of past research goes in two directions. One is like generality and versatility of the framework. So in the sense that you can cover many problems of a given family at the same time with the same framework and make it work in different metrics, more and more general metrics. So it's a very general approach. And that's the work of Aurora and Talloires. And they got a quasi-polynomial time approximation for TSP, Steiner 3, KMST, Steiner 4X, k-median, facility, etc. And for graph-based metrics, we don't have such a thing. It's a different perspective. Researchers have been getting efficient, problem-specific approaches, essentially. Like some of them generalized, but not as much as the Aurora and Talloires framework. So often it's a specific approach that handle TSP or handle Steiner 3 and subset TSP, but does not enter, for example, not cover KMST, for example, or does not tackle k-median and facility location. We need different approaches for these problems. So we have very fast way of solving the problem with Klein, with Bordale, Klein, and Mathieu afterwards, where Lee recently on PDAS for TSP minor free. So very good results. But there is no, and that's a frustration in the community, that there is no general framework for graph-based metrics that will cover many problems and also work beyond planar graph only. Because every time we get a result in planar graph, then it takes up to 10 years to get it into minor free if we get it. For now, it's only working for subset TSP, for which we got like a 2005 linear time PTAS for planar. And in 2020, we got a PTAS, which is not yet linear time. which was not yet linear time at the time, for CSP in minor 3. So there is a frustration of like getting a general approach. Okay, and so for example, KMST we don't know how to do in planar, and Steiner 3 and Steiner 4 we don't know how to do in minor 3. Okay, the result we have in this paper is precisely this general framework for designing network design problems in minor 3 metrics at the cost of a quasi-polynomial time, of course, like similar to the Talwar and Aurora original frameworks. So we are going to provide like a running time that is n to the poly log n, and get 1 plus epsilon for many network design problems, including KMST, for which getting the same bound for planar wasn't known before, even for planar, and getting, for example, the first p-task for Steiner 4s and Steiner 3 in minor 3 metrics. Okay, so now I'm going to try to give you the high-level approach and then go down into the details. So the high-level approach of Aurora and Talwar, and we are trying to kind of follow similar lines here. The general approach that they has was that you take your metric space and you try to find a representation of this metric space or an embedding of this metric space into a graph of bounded tree width. And because all these problems can be solved, most of these problems can be solved efficiently and up to optimality or half p-task for bounded tree width graph, once you have found your bounded tree width representation of the input metric, you can solve easily there. So you can summarize the ideas, and of course there is much more to get them work, but like at the high level, that's what's going to happen under the hood for this problem, for these approaches, is that you find a representation of the Euclidean space or the doubling metric with tree widths at most poly log n over epsilon, and such that the distances between points are preserved to 1 plus epsilon factor on average. And then once you have this representation, you can solve exactly on the resulting graph. Find the solution for this resulting graph will be a good solution for the original graph. Now, the issue you have with this approach is that the step 1 is very oblivious. The way it is done in Aurora and Talwar, it's a very oblivious way. It's not even problem specific. It's like, okay, there is a way to decompose the graph in such a manner that will give you bounded tree widths and that does not distort too much the distances. That's good. It's completely oblivious, very nice. But this step 1, completely oblivious that's there, is not feasible, cannot exist in planar graph. In fact, we have counterexample for this. So getting 1 to work in planar graph is impossible directly. So that's why it did not happen in planar graph before, because we don't know how to get there. So the solution we are bringing here is to do 1 and 2 at the same time. So essentially, we are going to decompose the graph into many possible bounded tree width graph. Okay, we're going to have n to the poly log n bounded tree width graph that we are decomposing, and we are saying, okay, one of them is going to be good for our solution and explicitly for our solution. So maybe many of these, it's not oblivious. It's going to be specific to the problem. Okay, so now let me dive into our approach. And our approach has two steps. So the first step is very similar to Aurora and Talwar, and we wish we can, it would be very nice if we can do the first step only, but we can't. But it's a very similar spirit. It's like there exists what's called padded decomposition, which are random decomposition of the graph into different pieces in such a way that for each edge UV, the probability that the edge UV is split in the sense that U and V are in different parts of this partitioning is proportional to the distance divided by the diameter. Distance UV divided by the diameter. So this is a very nice property, very useful for decomposing the graph, very specific to these simpler metrics in the sense that it doesn't exist as is with only constant factor proportional bound in general metrics specifically. And this decomposition will allow us to break the graph into pieces of smaller diameter and not have a low probability of splitting small edges. Good. So what do we gain out of step one? We gain something if the length of the solution, so this is where it becomes problem specific. So the length of the solution to the problem we are looking at is at most the diameter times log n over epsilon. Why? Because then what we are going to look at the expected number of edges that are going to be of opt that are going to be across different parts. So the number of edge UV that are in opt, so in this solution, such that U and V are in different parts, is in expectation at most the sum over all such edges times the probability that this edge is split, that U and V end up in different solution. And this is exactly our order of distance UV divided by the diameter. Now, if I sum this down over all the UV in opt, I get the length of opt divided by the diameter, which by our assumption here is at most log n over epsilon. So this is good because, and it's very problem specific. I mean, it's not problem specific, but it's specific to the fact that we are looking for a solution in this graph, right? Like we are not trying to get something specific that works for all pairs of edges, but just specific to the edges in opt. So if we try to decompose the graph into pieces that are satisfying this property, that in such a way with the padded decomposition, we are getting a decomposition that has small complexity when opt is not very long. And why? Because now we have these different partitions, but the number of edges crossing this part, the parts of the partition, is at most log n over epsilon. So that's good because what we can do is that we can keep these log n over epsilon edges that are in opt and delete the other ones. We don't care about the other one because they are not in opt anyway. So it's fine to look for a solution in the graph where we delete the edges that are not in opt. So there are only log n green edges that are across the partitions that are here, and these are the ones we keep. All the other edges across partition, we can move them. So now all these pieces of smaller diameter, they are connected only by log n over epsilon edges. So this starts to have small complexity. It has to behave like a bounded tree graph because it's a small separator. Like these log n edges are a small separator, given that we delete the other ones. Good. So of course, I'm assuming that I know opt and I can delete the other one given these ones. I don't know opt in reality. So from an algorithmic point of view, that's what I'm going to do. I'm going to take a padded decomposition and I'm going to look at all the possible sets of log n over epsilon edges that are across the part of my partitions. For one of them, I know that it contains all the edges of opt crossing the partition with good probability. Forget about the probability. Let's assume that this happens with priority 1, even though it needs more work to happen with higher probability, but let's not worry about that. What I'm saying is that pick a log n over epsilon size subset of edges crossing the partition. Over all these subsets, one of them contains the edges of opt, all the edges of opt crossing the partition. Okay? Look at this subset, delete all the other edges, and that's your new graph. Now, in this new graph, we can work in all the parts independently, given that these edges are in opt, because we know that we don't need the other edges. So we know that we can focus only on these log n. So we can try all possible p that are log n over epsilon size subsets of edges across the partition, and one of them is good. And for this one that is good, we would like to recurse. So we are going to recurse on all of them because we don't know which one is the good one. But that's the approach. Like we essentially break the graph using a padded decomposition. If opt is small, short compared to the diameter, we can remove many of the edges that are not in opt. We know that only log n over epsilon are in opt. Good. Okay, the next step is when opt is long. Okay, if opt is larger than the diameter times log n over epsilon, then we have too many edges crossing here. So it's too much guessing that we have to do. In that case, we give up. We cannot guess at them because it's many of them. So it's too many guesses to find out which edges are crossing and are in opt. So here we are doing something else. We are using different theorems in planar graph and minor tree graph. I mean, here actually it's only for planar. For minor tree there is more work, but I'm not going to go too much into that right now. So for planar, we are using the following theorem that says that there exists a shortest path separator made of 3 shortest paths. So UV is the shortest path, VW is the shortest path, WU is the shortest path. Okay, and such that the length of opt inside, so the total length of the green edges inside the separator, is roughly proportional to the length of the edges outside, within a factor of 2 of each other. So we know that there exists such a balanced separator. So if let's say I give you this separator, I tell you which one is the separator, then we can try to modify opt by creating a new solution opt prime, which is opt plus this shortest path separator. So I'm just increasing the size of opt. I'm not modifying opt more than that. I'm just taking opt and adding the shortest path, the 3 shortest paths. So now the length of opt prime, which is this new opt, is at most the length of opt plus 3 times the diameter. Okay, because these are 3 shortest paths, so it's at most 3 times the diameter. And this is at most, because opt is large compared to the diameter, this is at most 1 plus epsilon over log n times the length of opt. So I have increased opt. I mean, I'm looking at opt prime, which is just slightly longer than opt. So I'm very happy with that. So this is what we call the patching. We are modifying opt prime so that it behaves nicely. Of course, it's increasing the length of opt prime, but not too much. And why does opt prime behave nicely now? Because we can take this separator and work inside and outside of the separator independently, because we know that no matter what's happening in terms of connectivity inside, I'm adding the 3 shortest paths anyway. So I can kind of forget the connectivity pattern inside and the connectivity pattern outside when I want to solve. Okay, when I recurse on the inside, I forget what was happening outside because I know that anyway the whole boundary will be included. So it doesn't matter which pieces are where. Same thing for the outside. When I recurse outside, I know that I'm going to add this separator anyway, and that it's going to guarantee connectivity. So now we can independently recurse on the outside and the inside of the separator. The complexity, we don't need to know which are the connected components inside and outside. It's very simple. Good. So if the opt is very long at that step, we are changing our goal. We are not looking for opt anymore. We are looking for the solution opt prime. And from an algorithmic point of view, I'm going to try all possible set of 3 shortest paths. So there are n cube of them because it's 3 shortest paths. So I just need to find 3 vertices and get the 3 shortest paths. This gives me an inside and an outside. And I'm going to assume, for one of these choices, it's correct in the sense that the 3 shortest paths are all in opt prime. The 3 of them are in opt prime, and the inside and outside are balanced in terms of opt. Okay, good. So now I can repeat this process many times. I mean, I can repeat this process log n times because at each time I'm multiplying the length of opt by 1 plus epsilon over log n factor. So if I repeat log n time at most, I'm going to have a final opt prime that is at most 1 plus epsilon times longer than the original opt prime. So I can do it log n times. And the fact that I'm picking a balanced separator each time ensures that I'm going to repeat at most log n times. So the total error I'm going to get out of these patching steps is going to be at most log n 1 plus epsilon overall. Okay. So let me recap and prove correctness, then I'll prove complexity and I'll be done. So given a graph G of diameter D and where alpha is length L, we are going to do two things. We're going to find a padded decomposition, and for each, so that's partitioning the G into pieces, and for each tuple of log n at most of size at most log n over epsilon edges, I'm going to create a graph for this by keeping only these edges across the parts and removing all the other edges across the part. Okay, and then I'm going to take this graph and solve recursively in each part, assuming that the crossing edges are in out. Okay. For each of the, okay, and that's one step I'm doing. I'm doing another step in parallel, which is that for each choice of three shortest paths, so n cubed choices of shortest path separator, I'm gonna find a solution for inside and outside of each of them. Like, I fix a separator, find a solution inside and outside. Okay, independently. So again, making progress like this. And what I'm guaranteed by the argument that I described before is that there exists a near-up solution, such that depending on the length of this near-up solution versus diameter, either there is a tuple of edges across the things, across the part of the partition that contains n out, and there is no other edge across the partition that is in n out. So I can decompose. So this GP, for example, will be a good will contain n out, or n out contains one of the balanced separator and it's balanced with respect to n out. So I can make progress by picking this separator. Good. So along this line, so I know that among all the choices, that all the possible recursive calls I'm going to make, one of them is going to be correct. So I need to explore all of them, but I'm guaranteed that one of them is correct. So I need here to use dynamic programming to have something that is problem specific and that guarantees that I can get things correctly, but essentially, yeah, it's under the hood. Okay, so now the complexity of the algorithm is that the depth of the decomposition is log n, because either the length of odd decreases by a constant factor, or the diameter decreases by a constant factor, and these are both poly n. So after log n step, I'm sure I'm done. I should not decompose anymore. So when I'm doing step one, when I'm creating this padded decomposition and trying all tuples of size log n over epsilon, then the total number of graph GP that I'm creating is at most n to the log n over epsilon. So I have n log n over epsilon recursive call out of this recursive call. And for each of the n cube separator, I have like for each of I have one recursive call for each choice of three shortest path separator, so n cube recursive call. So overall, at each decomposition step, I'm creating n to the order log n over epsilon subproblems, and this process goes on for like log n steps, because after that I know I can stop. So the total number of subproblems that I need to solve in my dynamic program is at most n to the log squared n over epsilon, and so that's where the complexity is coming from. Okay, there is one way to extension to minor 3 is not as straightforward as it seems, because while step one is fine, you can have a padded decomposition to give you the exact same property you need. Step two is failing miserably because there may not be shortest path separator of length order diameter in minor 3 graph. So we need to do something else. In fact, we are also using padded decomposition in step 2 to decompose the graph using both shortest path and padded decomposition. So we have a more sophisticated patching process. It gives, at the end of the day, it doesn't change much. It just gives a worse constant in the running time, worse dependency on epsilon, but at the end, it's not very different. So the final result we get is a quasi-polytime approximation scheme for KMST, Steiner 4S, and these are the first results of this kind for minor 3. KMST is the first approximation scheme for planar as well. This can also be used to get like subset TSP, and so on in minor 3. So in fact, most of this connectivity network design problem can be solved using that framework. And we have this meta theorem that is not formally proven in the paper, but that is, by refactoring the ideas, one can prove, which is saying that you can get an alpha plus epsilon approximation in quasi-poly time for minor free if there exists an alpha approximation for bounded tree whiskers, because we need that eventually at the end. And for any, if you have this, if the fact that adding the patching step, which consists in adding shortest path to the solution, preserve feasibility. So if you have a solution, you start adding shortest path separator to the solution, and you preserve feasibility, then you can apply the technique and get an alpha plus epsilon approximation. And I'm going to stop here and thank you for your attention.